Okay, welcome back. So, if you recall, what we did yesterday, we were dealing with change of variables. Okay, change of variables. So then, what we did, we were assuming that there is a transformation from the UV plane to the XY plane, which transforms a region S to another region, R, through the transformation T, right? And if this transformation T is 1, 1, 1, 2, then the inverse of that transformation also exists, okay? And then you have seen that if I have to, find out, like this double integral in XY plane. So this turns out to be your f of x as a function of uv, y as a function of uv, and then your mod of the Jacobian, this uv and du du. It becomes this. Okay. So now you have seen that I have already noted down one exercise here. So what it is, you have to evaluate this integral, and you can see that the variables are x and y, and where r is the trapezoidal region with vertices 1, 0, 2, 0, 0, minus 1, and 0, minus 2. Now, one thing you have to remember, see here, what is being given is in this XY plane, So I have to search for how this region in XY plane would have looked like in the UV plane. Okay, so that because eventually you can see that we are going to perform integration in the UV plane. Okay, so the first thing is that what I'm going to do, I'm going to seek that free image, to be precise, free image of this region R in XY plane on UV plane. That is what I'm going to do. Okay, so just a minute, sorry. Okay, this is my XY plane, and this is a trapezoidal region with vertices. This is 1, 0, this is 2, 0, this is 0, minus 1, this is 0, minus 2. So basically, what I am going to have, something like this. So this is my region R. Okay, this is 1, 0, 2, 0. This is 0, minus 1, and this is 0, minus 2. Okay, so this is trapezoidal region. So now what I am seeking, it's pre-image in the UV plane. Okay. So now let us see what the boundaries are here. So then, as I have told you yesterday, that boundaries will correspond to boundaries, and so that I can easily find out the interior of the region with the help of that. Okay. So now let us call this maybe S1 bar. This boundary as S2 bar, this boundary as S3 bar, and this boundary as S4 bars. Okay. So now let us see what happens. So let us concentrate here, S1 bar. But again, before that, I have to define some transformation, isn't it? Right? I have to define some transformation. Okay.
Yeah.
So now, while you are going to define the transformation, what you have to do, you have to have a look at the integrand. Okay. So that is going to give you some way of finding out the transformation. And again, remember that the transformation doesn't have to be a unique transformation. So you can use more than one transformation to arrive at the same result. Okay, fine. So here it seems that because it is x plus y and x minus y. So why not try simply thinking u equal to x plus y and v equal to x minus y. Is it okay? Fine. So if we think about that, if we think that your transformation is u equal to x plus y, your v equal to your x minus y, so then obviously we will be able to find out x in terms of u and v, and similarly y also in terms of u and v. It is straightforward. Okay, fine. So now let us see under this transformation how we can get the region in the original UV plan. Okay, fine. So now look here. S1 is this. Okay, so here you can see that your y is equal to 0, right? And your x goes from
1 to 2.
1 to 2. Okay. So now, if I consider u and v, then you will see that what happens. Your if y is equal to 0, then u equal to v, it becomes x. Fine.
Yeah.
Isn't it? So basically, what we have to do in the UV plan. Now I am going to consider this line, u equal to v, because they are equal to x. So between one, see, x goes from 1 to 2. So this line I am going to consider x equal to 1. Right? If x equal to x goes from 1 to 2, I am going to seek the point. Okay, so when x equal to 1, u and v equal to 1, 1, right? Similarly, when x equal to 2, u and v they will be 2, 2. Is it okay? Fine. So basically, what I am doing here. So what I am doing, this is going to be my S1, and this line is simply u equal to v. Is it okay? Fine. Then so here this is it. U equal to v. Your S1. It becomes u equal to v between the points 1, 1, 2, 2, 2. Okay, fine. Now let us come to S2. Now, if you look at S2, this is a straight line, and the equation of this straight line is, if I consider this point, so it passes to 2, 0. So y minus 0 equal to minus 2 minus 0 divided by 0 minus 2 into x minus 0, isn't it? This is this equation of the straight line. Okay, fine. And minus 2 by minus 2, this is 1. So simply you are going to find it that this is y equal to no, just a minute. X minus 2. Because this is 2, 0 I have taken, right? Is it okay? Fine.
Yes.
So from here you will find that your x minus y equal to 2. X minus y equal to 2. So this line is x minus y equal to 2. Okay. So that means your v equal to 2. That makes your v equal to 2. Is it okay? Fine. V V equal to 2.
Yes.
And then if V equal to 2 and again here you can see that this straight line it extends from 0 minus 2 to your 2 0. Okay, so I have already got the equation for V. Now if I concentrate on U, so U will vary from x plus y, so U will vary from minus 2 to x plus y to 2. Is it okay?
Yes.
So that means your S2 is nothing but the straight line given by V equal to 2, and U in that case lies between minus 2 to 2. So your so it is going to be something like this. So this is my S2, where your V equal to 2. So similarly, I mean, we'll see that. So I mean, this S3, you will find that you can try it yourself. So this is going to be equal to U equal to minus 3. Okay, and this S4, this is S3, this S4, this is going to be V equal to 1, because this straight line is going to give you x minus y equal to 1. Is it okay? Fine. So we have found out the region. here in UV plan, and let me call it S. Fine. We have everything at hand now. Okay. Fine. So now if you want to perform the integration, so this is going to be now simply your S. Now this is E, this is U by V. Right? And then what you have to do here, this is going to be replaced by this mod of the Jacobian of xy with respect to UV. So now this UV, so this is simply del x del u del y del v minus del x del v del y del x, right? So from here I can see that del x del this is u, sorry, this is u. So del x del u, this is half, del y del v, this is minus half, right? And then del x del v is half, del y del u is half. So this is going to be minus half. Sorry, minus 1 by 4 minus 1 by 4. That means minus 2 by 4. So that is minus half, right? Okay. And if you take its mode, this is simply your half, and then du dv. Okay. So now look at S. If you look at this S, I mean, you can consider both as a type 1 region or type 2 region, isn't it?
Yes, sir.
Yeah.
Fine. Now you have to look at this integral. You have to look at this integral. So now, if I look at this integral, say suppose you want to integrate it with respect to your u, right? So then it is much more straightforward. If you want to partially integrate with respect to u, This is simply going to give you what? I mean, 1 by v e to the power e by v, isn't it? Right? Okay?
Yes.
So basically it is v, v into this. But if you want to integrate it partially with respect to v, I mean again, it is not going to be that straightforward. Isn't it? Right?
Yeah.
So that is why I would like to integrate with respect to u first. Okay. So if I want to integrate with respect to u first, then I must have here u as some function of v. I mean say g1v and u as some function of g2v, and then I will have fixed limit for v, and then I will have something like this. Is it okay? Fine. So, isn't it? So basically,
Yes,
what
sir.
we have to consider this as a type 2 region. Okay. So if it is type 2 region, so then I have to look for left to right. I have to look for left to right. Okay. So this is what it is going to be. What it is going to be. So let me keep it like this. What it is going to be. It is going to be like say this is with respect to, so u equal to, and you can see that the left boundary it is simply minus v and right boundary is v, and maybe I'll bring that up here, and then e to the power u by v du and dv, and you can see that your v simply goes from this 1 to 2, isn't it? So v equal to 1 to 2, and you can easily integrate it. You can easily integrate it. I don't want to spend much time on that. I have already told you. So basically, what is going to happen? So you are going to get half. I mean v e to the power u by v. So then this is what on. So then once you plug in u equal to v, let us write with u equal to v minus v. Then otherwise you may get confused. So if you plug in u equal to v, this is simply e to the power 1. If you plug in u equal to minus v, it is e to the power minus 1, isn't it? So eventually you are going to get half this, and then integration of 1 to 2 v dv, right? So, okay. So here, what was happening when we used, set of variables, and then the double integral, it eventually becomes this. And once you work it out, then you can see that, this is going to give you, after integration b squared by 2, so eventually 4 square minus 1, that is 3 by 2, along with this half. So the final answer is going to be your e minus e to the power minus 1. Okay, fine. So now you can see that, we used the Jacobian approach in order to find out this integral, and the Jacobian, for this particular example, it turned out to be half. Okay. Now the thing is that here in this particular case, the transformations are already known, and they are kind of pretty simple to work it out. What I mean to say is that, once you have u and v in terms of x and y, obviously the reverse transformation of x and y in terms of u and v, they were pretty straightforward. Okay. But there may be some cases in which it is not that straightforward, and probably you won't like to again do the reverse transformation. So what do? In fact, there is a property of these transformations if they are 1, 1 and on 2. So that means if the inverse transformation exists, so then what happens? The Jacobian of xy with respect to uv, and if I take Jacobian of uv with respect to xy, their product, I mean, it would have given me 1. So there is a property like that. So you may be thinking, I mean, what is the utility of this property? Now, suppose we were completely unaware of, I mean, what was the inverse transformation here? What was the inverse transformation here? So then you would see that if I want to find out your Jacobian of uv with respect to xy, so this would have been simply del u, I mean del x, del v, del y minus del u, del y, del v, del x. Okay, and you have seen that from here your del u, del x, this is simply what? Del u, del x is 1. Del v, del y, it is minus 1, and again del u del y it is 1, and del v del x it is again 1. So eventually this would have given you minus half, right? So now if you plug this minus half in here, so then you can easily see that this Jacobian of this uv, Jacobian of xy with respect to uv, that is going to give you simply minus half, and that is exactly whatever we have got it for this one. Remember, this was there the determinant of the Jacobian, and that is why it has become half instead of being minus half. Okay, fine. So in this way also you can move forward. Okay. So now let me come to the Jacobian of a transformation, I mean involving your 3 variables. So basically, in those cases, what we are going to do, we will consider, I mean, a transformation, say from something like your UVW plan, to say, suppose your X, Y, Z plan. Okay, so what is going to happen? Earlier, if you think about a two-dimensional region. Okay, so then what was happening? We had considered everything on a plane. So now we are considering everything on space, right? And over there, the region under consideration, it was what? It was a planar region, right? But here, the region is going to be some kind of a solid region here. Say, suppose I am considering a region S here, and that S, it will be transformed into another region R in your XYZ plane. So basically, it is going to be something like this. Okay. And again, what you can do, you can use the change of variable concept in order to find out the triple integral. Okay. And over there, it is going to be something like this. Say, suppose I am trying to evaluate a triple integral, say something like, say, your phi xyz, and so this is going to be dv, so then, and this is going to transform into your R2s. Okay, and then you are going to plug in this phi. So x is going to be a function of, I mean, UVW. Y is again going to be a function of UVW, and Z is again UVW, right? And then what is going to happen? You are going to get Jacobian of your XYZ with respect to your UVW, right? And then simply this part is going to give you your du, dv, dw. Okay, so all this stuff we are going to see more systematically in our slides. So, and likewise, the way we define the Jacobian for a function of two variables. So the Jacobian for a function of three variables. So three variables. So it is simply going to be this one. It's pretty straightforward. Dx du and dy du, dz du. So dy du, dy. Sorry. Dx dv, dy dv, dz dv, and similarly dx del x del w, del y del w, and del z del w. It is simply this determinant. Okay, so in this way we can find out, and we are definitely going to take an example. I mean, don't worry about it. We have already done this thing. In fact, I mean, spherical polar coordinates, right? And we were using some kind of direct method, and at the time I told you that okay, we are going to find a unified way of arriving at a formula. And in fact, I mean, this gives you that formula. Okay, so now we are going to move on to our slides. Example that we were considering, and this is what I told you about this node. Okay, so this comes from the consequence of chain. Okay, so now so this is the answer. Yeah, so now let me come to triple integrals. So, as I have told you, there is similar change of variable formula for triple integrals. If T is a transformation that maps a region S in UVW space onto a region R in XYZ space by means of the equation. So, this is say X is a function of UVW, Y is also a function of UVW, J is a function of UVW. So, the Jacobian T is the following 3 by 3 region, and this I have already told you. And then whatever hypothesis we have used earlier, then we will have the following formula for taking triple integrals. Okay, so I mean, if you consider the integral in the original plan, so then this will be converted into simply this. Okay. So, I mean, now what I'm going to do, because I know this formula, as promised, what I'm going to do, now we are going to work out one example. Suppose we have to find out this triple integral into the power x squared to the power 3 by 2, and simply dv, okay, and where b is nothing but the unit ball, I mean, given in terms of your rho, theta, phi, and this is given by your rho, theta, phi, such that your rho lies between 0 and 1, theta lies between 0 and 2 pi, and your phi, it lies between 0 and pi. Okay, fine. These have been given in spherical, I mean, polar coordinates. Okay, and just let me give you a quick recall of what we did in spherical polar coordinates. Like suppose I consider the XYZ plan, and if I consider a point in space, and if I assume that the point lies on the surface of the sphere of say radius, sphere of radius rho, sphere of radius rho. So then what we were doing, we are simply, dropping a perpendicular, say PL from the point P on your xy plane, okay? And then we join the origin with the foot of the perpendicular, and suppose the distance OL is simply R, and if this OL makes an angle theta with x-axis, and this radius vector OP, it makes an angle phi, with the z-axis, then you know that the transformation was simply your x equal to rho sine phi your cos theta, and y equal to rho sine phi sine theta, and j equal to rho cos phi. Okay, and now if I want to find out the Jacobian of the transformation of xyz with respect to your rho theta phi, so then this is simply going to be the determinant, your del x, del rho, del x, del theta, del x, del phi, similarly del y, del rho, del y, del theta, del y, del phi, and del z, del rho, del z, del theta, and del z, del rho. And if I plug this in, here, del s, del rho, this is sine phi cos theta, then this is minus sine phi sine theta, and lastly it is going to be rho cos phi cos theta, rho cos phi cos theta. Okay, and similarly you can plug in the other 6 entries here, and I don't know whether you have already worked it out or not, but if you work it out at home, you will see that this turns out to be your rho square sine phi. You can easily find it out. And again, I think in the last example that I worked out, like in the 2D plan, I think I had something like e to the power x plus y, x minus y, d8. Remember, I think I just when I was telling where this half came in calculation, I said that half was the determinant. It is not only determinant, it is the absolute value of the determinant. Remember that, okay? It is not simply determinant, because in the original determinant it was minus half, okay? But because it was absolute value of the determinant, that is why it became plus half, okay? Please note that, okay? So now, see, if I want to work out this example using the change of variables approach, So then you can easily see that what this is going to become in r theta r theta phi, I mean space, okay? So then this is going to be what? If the transform region, say suppose I call it say B1, say, right? So then this is going to give me simply x square plus y square plus z square equal to your this, okay? And instead of dv, what I'm going to get? I'm going to get del this, the Jacobian your rho theta phi, this absolute value, and then simply d rho d theta d phi, d phi, okay? And eventually you will see that this is going to become again just a minute. In the original reason, do I? Okay, fine. So then your, because they have used B as this, which is given in the rho theta phi. Let me keep it like B only. Huh? Let me keep it like B only. Okay, fine. So then this becomes rho cube, and you know that this is rho square sine phi, and then d rho d theta d phi, and the limits of your rho theta and phi is as given by this, so we don't need to worry about this. And now you can see that, I mean, the derivative of sorry, it is e to the power derivative of rho cube, it would have been 3 rho squared. And again you will see that all the functions here, they are of variable separable type. The eventual function, it is nothing but product of 3 functions of your rho, theta and phi, right? And each of those functions can be separated out in terms of, like it becomes something like a function of rho, a function of theta, and a function of phi, where this is simply your rho square e to the power rho cube, this one is 1, and this one is what? This one is simply sine phi. Okay, so if I want to work it out, you already know how to go about it. We can easily separate the variables. So this is going to be your rho going from 0 to 1, right? And then rho square e to the power rho cube, maybe I can write it as 3 raised to rho square 1 by 3. So, and this is 0, and then simply 0 to 2 pi, I mean d theta, and then what is going to happen? 0 to pi, your sine phi, 0 to pi sine phi d phi. Okay, and you can easily work it out. Because this is eventually going to give you what? 1 by 3 e to the power rho cube. I mean rho going from 0 to 1. This is simply, you know, this is 2 pi, and this is minus cos phi, 0 to pi. And eventually this is going to, I think, 4 by 3 pi e minus 1. This is, you can easily work that out. Okay, you can easily work that out. So then I mean, we are going to work out one more example. Okay, if possible, let me get back to the slides again. This is the ice cream cone example. Okay, so what was happening here? It was, let me just simply draw it for a while and then I'll come back to it. Okay. This was okay. Now I'm going to show you some figures here, but let me tell you, I mean, how to work out the limit. So here you have to simply find out the volume of the solid that lies above the cone given by j equal to square root x square plus y square. You can already see the figure for that. And the sphere x square plus y square plus j equal to I mean x square plus y square plus z square equal to j. So basically, this is a sphere with center 0, 0, half, right? 0, 0, half, and radius radius half. Okay, so it is. So let me just come out of this. So I have a situation like this. I have a situation like this. So basically, I want to find out the volume of this shaded portion. Volume of this shaded portion. So what I have to do, I have to simply integrate. I have to simply integrate the function 1 over this region E, where E is divided by this shaded portion. I mean, the yellow E is nothing but the shaded region. Okay. So now, what I would like to do, and of course, since we are using, spherical polar coordinates, so your x equal to rho sine phi cos theta, y equal to rho sine phi sine theta, and z equal to rho cos theta. Sorry, cos phi. So now here, if I look at the sphere, given by this, so then you know that under the given transformation, this is going to be rho square, and this is going to be rho your cos phi. Okay. So from here, I'm going to get rho equal to 0 cos phi. Okay. So that means the lower limit or upper limit of rho is going to be 0 and cos phi. Okay, fine. See, we considered, type 1, type 2, type 3 regions in 3D space, right? So here we have already got our kind of surfaces, okay, which is going to bound your rho. So now what is happening out here? And you will see that this is a function of phi. Okay. So now again, if I consider the cone under just a minute. So for the cone, your z equal to square root x squared plus y squared. So this is going to be z. Z is what? Rho
cos phi.
And this is simply going to be rho sine phi. You simply look at the transformation. Because cos squared theta plus sine squared theta, that is going to give you 1, right? And from here, what you are going to get, you are going to get, tan phi equal to 1. So this means your phi is going to be equal to pi by 4. And in fact, this is obvious that, so this angle is nothing but phi, isn't it? So here you can see that phi is going to go from 0 to pi by 4. 0 to pi by 4. Okay, fine. So we have already got all the information, and you know that theta, it is going to go from 0 to 2 pi. So let me simply show you that. So this is what it is. Rho varies from 0 to cos phi. Okay. Rho designates the radius of the sphere. If you consider a point to be lying on the surface of the sphere, okay, then phi varies from 0 to pi by 4, and theta varies from 0 to 2 pi. Okay, fine. So now I'll just simply show you the way how to integrate it. That's it, because we have got everything. So now, if I have to integrate this, so then again, if I use transformation, so then you have 1 into rho squared sine phi, then the rho d phi d theta. So for rho, I am having 0 to cos phi, and then for phi 0 to pi by 4, and then your theta 0 to 2 pi. Okay, so I have got all the information, so you can easily integrate it. Okay, this integration is not that difficult. Only thing is that you cannot separate the variables out. You have to remember that, because now you can see that here the upper limit is a function of phi. Is it okay? So if I maybe I will just simply do, once more step. So this is going to be what? This is going to be what? Your rho cube by 3, your sine phi, and rho goes from 0 to cos phi, then d phi, d theta. So now you know that this is pretty straightforward, because what is going to happen when rho is when you are going to replace rho with cos, because you are getting cos cube and you already have sine, right? D of cos phi is minus sine phi, so it is beautifully said. So you can easily, I think the answer is pi by 8. Please work it out. Okay, fine. So this is about your triple integral. This is about triple integral. So now what I'm going to do, I'm going to go to vector field. I'm going to go to vector field. So firstly, I'm going to show you some examples and I'm going to give some definition. And then you may be a little bit surprised that I'm going to directly jump over line integrals. And the thing is that, line integrals, it hasn't come out of blue. Okay, you may be thinking, I have started with vector field and then I have jumped into line integral. Why it is so? Because eventually, what I am going to do, I am going to come back to line integrals of your vector functions. Okay, so that is why this is important. Okay, and because this is going to help me later on in doing your surface integrals as well. Okay, fine. So let me quickly browse through some slides. So this is about vector field. This is about vector field. Okay. Now, what is a vector field? Okay. See, firstly, what do we have to do? We have to think about some domain. You consider it, more precisely in 3D, so it is going to be much more, practical. Okay. So, for the time being, let us consider a 2D domain. So here you can see the Nova Scotia, and this is a part of Canada. And here you can see it is the ocean current. And ocean current, they have been designated by the velocity vectors at different locations in that geographical area. So you can see that there is what there you can see some vector. You can see some vector. And similarly, this is nothing but a cross section of an aerofoil. And in fact, I'm happy to tell you that this is from my own research. And here again, all these vectors that you see, they also designate velocity. And this one is the kind of configuration of a typical tornado. Again, you can see that the way these vectors comes out, you can see in one direction the tornado is moving. Okay, so it is kind of some whirlpool structure, and then it is going up and so on. And this is an actual picture of a tornado. So all these are related to what we call as vector fields. Okay, because now you think about the very first figure. So in the first figure, what we had, I have shown you Nova Scotia, basically some Bay Area. So this is the Bay Area. In fact, this is near the Golden Beach in San Francisco. So over there also, it is showing the. I think it is not ocean current, but it is the velocity of air around the region. It has been designated by these factors. Okay. So all of this, what it is doing, we are considering a domain, right? And in this particular case, right now, what you see in this domain is a two-dimensional domain. So if we consider each point of that domain, so what we can do, we can define a vector there, and that vector, I mean, if it is in two-dimensional plane, that vector we can consider as a function of x and y. And if it is in three-dimensional space, if you have a region in 3D, and in that region at each point, if you can consider a vector which can be described as a function of those three variables x, y, and j, then we say that it defines a vector field in that region. Okay, so this is what it is. Say, for example, this is in 2D. What is happening? I'm considering maybe here the whole I mean R2, and each point in R2 through some formula. I'm going to show you some typical formula later on. So what we have done, we have defined a vector at each point. Similarly, here in 3D, at each point, I'm defining a vector. Okay, fine. So basically, what is going to happen here? If I consider say this vector at the point x, y, z. So what is going to happen? So this vector, I can express it. To be what? To be something like I mean f1i plus f2j plus f3k, right? So what is going to happen? So that means this length is going to be f1i. Sorry. This length is going to be f1. This length is going to be f2, and this length is going to be f3, right? So then is this length going to be f3? Are you sure this length is going to be f3? It is not, because I'll be starting here. Okay. So what is going to happen? I'm going to consider a plane parallel to the height of this j, and over that plane I can consider this same situation. Okay. But anyways, see, I'll come back to that again. I mean, it will be more clear, because now maybe I'm confusing you with it. So this is the definition of a vector field in R3. So if E is a subset of R3, then a vector field on R3 is nothing but a function f that assigns to each point x, y, z in E a three-dimensional vector f. Okay. So in fact, what happens out here is that, like say, I mean, suppose I am considering a region E in R3, right? And for each point x, y, j belonging to this region E, if I define a vector, say f, say this to be something like f1 x, y, j I plus f2 x, y, z j plus your f3 x, y, z k. So then this vector f itself is going to be a function of f, y, z. Okay. So that means through this formula, at each point x, y, j in E, I can define a vector. Okay. Fine. So that is what is going to define a vector field in the region E. That's it. So now let me consider a typical example. For example, say suppose let me consider a vector field in R2, and it is given by say this is minus yi plus x. Okay, fine. So now let me tell you how to work this out. This is x. This is y. Oh, say suppose this is 1, this is 2, 1, this is 2. Okay. Okay. Say suppose at this point, at this point 1, I want to define a vector under this formula. Okay. So then this f11, this is simply going to be minus 1i plus 1j. Is it okay, everybody?
Yes,
Fine?
sir.
Yeah.
Fine? So then that means what we have to do. You start here at this point. You move 1 unit towards left because this is minus 1 and 1 unit up. So this is the vector. This is the vector f at 1 1. Is it okay? Fine. And suppose at this point, say 1 1 0, or maybe I should take something else. Maybe at this point, say 3 0. Say at the point 3 0, I want to find something. 3 0. So then this is going to be what? Minus 0i plus 3z. Am I correct? Right? So if you want to define a vector here, so it is simply going to go 3 unit up. 1, 2, 3 unit up, something like this. Is it okay? So similarly, say suppose I want to have another vector here. Say so this point is say minus 1 1. So if you want to have it f minus 1 1, so it is going to be what? Minus 1i minus 1j. Okay, so that means what you have to do, you have to come 1 unit towards right and again 1 unit down. So this is going to be your vector at minus 1 1. Is it okay? Fine. So this is the way it is going to work. This is the way it is going to work. So now I'm just going to show you some more examples. So it is something like that. In fact, this is the this is called the rotational vector. Okay, if at each point, I mean, you draw those vectors, then it is going to look like this. So here you can see that in fact, all these vectors is designating some kind of rotation. Okay, so similarly, I mean, in 3D also, you can have, say, for example, this figure. I mean, what you have to do, you simply take a point, fixed point, say, and at that point, you simply run through the vector and you'll be able to draw all these vectors. Is it okay? Fine. So now can you tell me, I mean, these were difficult. I mean, 10, 11, and 12, they were obviously more difficult to draw than the one you see in the very first figure. So can you tell me in the first figure, I mean, what could be the function that defines this vector? What is so special about these vectors?
So it is 0i minus 1j.
1j.
1j or something else.
Minus yj.
See here, all the vectors. All the vectors, they are in which direction?
Downwards
Or
and upwards.
downwards or upwards?
Yeah.
Isn't it?
Yeah.
They are in the direction of j.
Yeah.
Right? So x and y component of them must be 0.
Okay, yeah.
Isn't it? And j, it looks like, I mean, if you increase the value of j, the length of the vector is also increasing, right? So it seems like this is nothing but j k cap. The function is simply it is j k cap. Because you can see when the value of j is less, the length of the vector is also less. Okay, fine.
Yeah.
So in this way, we can define. Vector. Okay. So this also I am going to simply run through what are gradient fields. Now we have already discussed earlier. I mean, in directional derivative, what we did, we defined some gradient vectors. So if you consider a scalar function f, if f is a scalar function of two variables, then you can see that, I mean, that f, it defines a vector field in fact, because it defines a function of x and y, right? And that means at each point we will be able to draw a vector through this formula. So this vector is nothing but gradient vector. So it defines a vector field in R2, and that vector field is called gradient vector field. So likewise, if f is a scalar function of three variables, its gradient is a vector field on R3, and you know it is given by this. So these were the things about your vector fields. So next, what I'm going to do, I'm going to deal with your line integrals. So maybe I'll stop here. So in my next class, I'm going to deal with line integral, and then I'm going to go over the line integral of vector function. So that's what I'm going to do. So then I will meet you in my next class.